Have you ever looked up at the night sky and felt a kind of quiet awe? That deep sense of mystery, where the stars above seem not just like lights in the sky, but as doorways to something much grander, much stranger than anything we could possibly imagine. You are not alone in feeling that way. The universe is vast, so vast it defies comprehension. And within that vastness lies not just beauty, but strangeness. Things so bizarre, so completely outside our everyday experience, that they challenge the very limits of our understanding. Tonight, as you settle in, allow your thoughts to drift gently into that darkness. Let the worries of the day fade away. Let the tension leave your body. Feel yourself floating, weightless and calm, through the boundless reaches of space. Your breath slows, your mind quiets, and the stars begin to speak. This is a journey into the most bizarre phenomena in the universe. Phenomena that remind us just how little we truly know about reality and how much more there is to discover. So close your eyes. Let your imagination unfurl like a solar sail in the windless void. And together, let's begin our voyage. We often think of space as a void, silent, dark, utterly empty. It's an image that feels so intuitive, so comforting in its simplicity. We picture astronauts floating through a black expanse, light years from the nearest object, surrounded by nothing at all. But in truth, this idea of nothingness is an illusion. In the strange world of quantum physics, even the vacuum of space is not truly empty. In fact, it might be one of the most active places in existence. This strange reality is governed by a principle called quantum vacuum fluctuations. It's a phenomenon so bizarre, it seems pulled from science fiction. According to quantum field theory, every point in space is filled with invisible fields, fields that ripple with energy, even in the absence of matter or radiation. And from these ripples, particles can spontaneously appear and disappear. Not metaphorically, literally. These particles, called virtual particles, exist for only the briefest moment. They appear in pairs, one particle and one antiparticle. They burst into being from the vacuum, annihilate each other almost immediately, and vanish again into the nothingness from which they came. You'd think something so fleeting couldn't matter. But the universe doesn't agree. These ephemeral fluctuations are powerful enough to produce a very real, measurable force known as the Casimir effect. If you place two uncharged metal plates extremely close together in a vacuum, mere micrometers apart, they will mysteriously be drawn toward one another. Why? Because the energy of the vacuum between them is slightly less than the energy outside, thanks to those buzzing virtual particles. The plates are nudged together by the energy imbalance, by the vacuum itself pressing in. But the implications go even deeper. Some physicists believe that quantum fluctuations might have actually sparked the Big Bang, the moment when space, time, matter, and energy all sprang into existence. According to this theory, a fluctuation in the quantum vacuum could have caused a bubble of space to expand rapidly in a process called cosmic inflation. From this infinitesimal bubble came the entirety of our universe. Think about that for a moment. Everything we know, every star, every planet, every atom in your body, may have emerged not from a divine hand or a cosmic explosion, but from a tiny twitch in the fabric of nothing. Even now, these fluctuations are believed to contribute to something called dark energy, a mysterious force that causes the universe to expand faster and faster. We don't understand dark energy, but it may be woven into the vacuum itself, quietly rewriting the future of the cosmos. So the next time you hear someone say, "There's nothing out there," remember the vacuum that isn't empty. Remember the quantum sea that churns beneath the surface of reality, and the particles dancing in and out of being like fireflies in the night. And as you let this thought settle into your mind, you might just feel it, that sense of wonder, of drifting not through emptiness, but through mystery. Rogue planets, lost worlds, adrift in the dark. When we think of planets, we naturally imagine them orbiting stars. Just as Earth circles the sun, we assume that every planet must be tethered to some warm, radiant center, a sun that gives it light, heat, and the possibility of life. But the universe, as always, has surprises in store. There exists a class of planets unlike any we were taught to imagine. They are called rogue planets, and they wander the galaxy alone, untethered, unanchored, and silent. These worlds are not bound by the gravitational embrace of a parent star. Instead, they drift freely through the interstellar void, wrapped in darkness. And what's most astonishing is that they may be far more common than we ever believed. Astronomers now estimate that there could be billions, perhaps even trillions, of these rogue planets in our galaxy alone. That's more than the number of stars. Some may have formed normally within star systems, only to be ejected by violent gravitational interactions, collisions, near misses, or the chaotic shuffle of newborn worlds fighting for stability. Others may have formed in the darkness itself, never having known the light of a star. Imagine one such world, larger than Jupiter, its surface a swirling storm of ammonia clouds and high-pressure winds. Beneath its clouds, lightning flashes with no one to see. Its gravity crushes down on anything that enters, yet its core glows faintly from internal heat. Without a sun to warm it, this world would seem to be a frozen wasteland. But strange as it sounds, rogue planets may not be entirely cold. Some of these drifting giants may retain heat for billions of years, thanks to the radioactive decay of elements in their core, or the residual energy left from their formation. Others, particularly those with thick atmospheres, may trap this heat and create subsurface oceans beneath icy shells. These oceans, isolated from the cosmos, may swirl with heat and chemicals, ideal conditions for the emergence of life. It's a thought that challenges our assumptions. We've always associated life with starlight. But what if life can emerge in the shadows? What if under the ice of a rogue planet, far from any sun, entire ecosystems are thriving, blind, slow-moving, alien, creatures that evolved in permanent darkness, never having seen the light of a star, communicating through vibrations or bioluminescent pulses? We've already found hints of this kind of life on Earth. At the bottom of our own oceans, near hydrothermal vents, exist entire communities of organisms that have no reliance on sunlight. They draw energy instead from the heat and chemicals expelled from the Earth's crust. These are extremophiles, life forms that thrive in what we once thought were unlivable environments. If they can live here, why not on a rogue world? Some rogue planets may even carry moons, trapped companions circling a nomadic king. These moons could experience tidal heating, a frictional warmth generated by gravitational forces, much like Jupiter's moon Io. This, too, could support subsurface oceans and geological activity, another cradle for life in the cold. From time to time, a rogue planet might even pass close enough to another star to be briefly illuminated. For a few fleeting centuries or millennia, its surface might glow in the starlight before slipping once more into darkness. In that moment, life might bloom or perish. A brief candle in the infinite night. Now imagine drifting through the galaxy with one of these worlds. There is no sunrise, no seasons, No time marked by the dance of a day, only a sky full of stars, uncaring, unmoving. The planet's only warmth comes from within, and life, if it exists, knows nothing but the slow rhythms of the deep. So when you lie back tonight and gaze into the night sky, think not just of the stars, but of the spaces between them. There, in the silence and the dark, entire worlds may be wandering, untouched, unseen, and perhaps not alone. Neutron stars, the crushed hearts of giants. Out in the distant arms of the galaxy, in places where light flickers and gravity reigns supreme, lie some of the strangest objects ever discovered: neutron stars. These are not just stars. They are the corpses of stars, remnants of once glorious giants that burned with unimaginable energy, only to collapse in the final stages of their lives into something profoundly alien. A neutron star begins its life in fire. After a massive star has fused its atoms for millions of years, creating heavier and heavier elements, it finally reaches iron, the element it can no longer extract energy from through fusion. When this happens, the delicate balance between gravity and internal pressure breaks. In an instant, gravity wins. The core collapses. The outer layers explode in a cataclysm known as a supernova, one of the most powerful events in the universe. What remains at the core is no longer a star in the traditional sense. The immense gravitational pressure has crushed electrons and protons together, creating neutrons. The entire mass of the core is compressed into an object only about 12 to 15 miles in. Diameter, roughly the size of a city. But don't let its size fool you. A single teaspoon of neutron star material would weigh billions of tons. That's the weight of every person on Earth combined, dozens of times over. This density is so extreme that atoms themselves no longer exist in their familiar forms. The matter is now a tightly packed sea of neutrons, held together by gravity so intense that even light bends around it. If Earth were the size of a peanut, a neutron star would be a grain of rice with the same mass. Some neutron stars spin at incredible speeds, rotating several hundred times per second. These are known as pulsars, and they emit beams of electromagnetic radiation from their magnetic poles. As they spin, these beams sweep across the universe like a cosmic lighthouse. From Earth, we see these as rhythmic pulses of light, remarkably precise, sometimes more accurate than atomic clocks. Others possess magnetic fields so powerful they defy comprehension. These are magnetars, and their magnetic fields are trillions of times stronger than Earth's. If a magnetar were located just 1,000 kilometers away, it could erase the data on every credit card and hard drive on Earth. Closer still, and it would disrupt the atomic structures in your body. Thankfully, magnetars are rare and distant, their strange violence unfolding far beyond our fragile world. But perhaps the most unsettling thing about neutron stars is how little we truly understand them. Inside, beneath the crust, physics becomes murky. The pressure is so intense that the very nature of matter may change. Some theories suggest that at their cores, neutron stars might harbor quark matter, a strange soup of elementary particles stripped of all structure. Others even speculate about the existence of strange matter, an exotic form of matter that could be more stable than anything known in the universe. If strange matter exists, it might be contagious. In theory, if a neutron star made of strange matter came into contact with normal matter, it could convert it, turning everything it touched into more strange matter. One tiny speck of this substance, if it landed on Earth, could hypothetically transform the entire planet in a flash. This, of course, is purely speculative, but the fact that such ideas are even plausible hints at how mysterious and potentially dangerous these objects are. Yet despite their terrifying properties, neutron stars are hauntingly beautiful. Imagine standing on a rocky moon, watching a pulsar rotate in the sky, sending beams of light sweeping across the void in perfect rhythm. Each pulse a heartbeat, each flash a reminder that something so small, so dead, can still dance across the cosmos with unimaginable power. In the endless expanse of the universe, neutron stars are like tombstones of the stars that came before us. But they are not quiet. They spin, they pulse, they radiate, they endure. And as you drift further into sleep, know this: somewhere out there, a city-sized star is spinning silently in the dark, its rhythm precise, its gravity absolute, its mystery eternal. Neutron, stars, strange moons, starquakes, and the edge of physics. Though neutron stars are often imagined as solitary, spinning ghosts of stellar pasts, some of them are part of cosmic duets. These binary systems, where a neutron star orbits another star, or even another neutron star, are cosmic laboratories where gravity pushes matter to the brink. In a neutron star-white dwarf binary, the neutron star can pull matter off its companion, feeding on it like a stellar vampire. As this matter spirals into the neutron star, it forms an accretion disk, heating to millions of degrees and emitting powerful X-rays. These systems are known as X-ray binaries, and they shine with an intensity that can outshine entire galaxies, despite being only a few kilometers across. But not all binaries are so polite. When two neutron stars orbit each other, they slowly spiral inward, losing energy through gravitational waves, ripples in space-time, first predicted by Einstein and only recently detected directly. These waves, so subtle they stretch space by less than the width of an atomic nucleus, tell us about the invisible dramas unfolding in the deep cosmos. Eventually, these stars collide in a spectacular event called a kilonova. When they do, the explosion is so intense that it forges heavy elements, gold, platinum, uranium, and flings them into space. It's quite likely that the gold in your jewelry or the uranium in nuclear reactors was born in the fiery death of a neutron star collision. Think of that for a moment. The shining elements we hold so precious were born in the merging hearts of dead stars. But neutron stars aren't only dramatic when they collide. Sometimes they tremble. These tremors are called starquakes, and they occur when the crust of the neutron star suddenly shifts, cracking under the immense pressure of its magnetic field or rotational stress. Unlike earthquakes, which might shake a city or rattle a continent, a starquake can release as much energy as all the earthquakes in human history combined within a single second. These starquakes can cause sudden changes in the rotation of the neutron star, known as glitches, revealing that even these cosmic lighthouses are not immune to sudden shifts in their internal structure. What could possibly cause such a quake? Consider that the outer layer of a neutron star is believed to be a solid crust, one of the strongest materials in the universe. A crust so dense, a cubic centimeter would weigh 100 million tons. And yet, even this structure cracks under the intense forces within. Then, there's the riddle of the neutron star surface. Is there one? What does it even look like? If you could approach a neutron star, an impossible task, given its lethal gravity, you might find no true surface as we understand it. Instead, you would encounter a thin atmosphere, just millimeters thick, glowing with X-rays, layered atop a crust of neutron-rich nuclei. Beneath that, as you descended through the incredibly compressed layers, atoms would dissolve, neutrons would become free-roaming, and the fabric of matter itself would change. Some scientists speculate that at the very core, the density becomes so extreme that neutrons themselves break down into their constituent parts, quarks, creating a sea of unconfined particles called quark-gluon plasma, a state of matter last seen in the moments after the Big Bang. If this is true, then within neutron stars lies a glimpse into the very birth of the universe, frozen in time, waiting to be understood. Still more mysterious are the exotic particles that may exist under such conditions. Bosons, hyperons, kaons, particles that decay quickly on Earth, may find stability inside neutron stars. These hypothetical configurations of matter hint at a whole hidden universe within a sphere no larger than Manhattan. And let's not forget their gravity. If you stood atop a neutron star, somehow immune to the crushing pressure, you would weigh 1 billion times more than you do on Earth. Time itself would slow dramatically. 1 second on the surface could be hours elsewhere. This is gravitational time dilation, a real effect of general relativity. The deeper you are in a gravitational well, the slower time passes relative to the rest of the universe. If you looked up, the sky might warp around you, bent by the gravity into a perfect sphere of stars. Space would not be space as you know it. It would feel like looking out from within a deep, invisible well, with reality itself bent at the edges. As you settle deeper into rest, let these strange truths wash over you. Let your imagination linger on that glowing sphere in space, silent, heavy, ancient. A place where time slows, matter collapses, and the rules of the universe are rewritten. A place where the dead still spin, casting their silent rhythm across the dark. Black holes. Gateways to the unknown. Few things in the universe inspire more awe, more fascination, and more mystery than black holes. They are the ultimate paradoxes of nature, invisible yet detectable, empty yet unimaginably heavy, destructive yet perhaps gateways to deeper truths. Black holes are cosmic riddles wrapped in darkness, places where the known laws of physics break down and where our understanding ends. To begin imagining a black hole, forget everything you know about matter. These aren't stars or planets. They are the end state of mass collapsing into itself under the relentless pull of gravity. Take a star several times more massive than our sun. Let it burn through its fuel, collapse in on itself, and you get a point of infinite density known as a singularity. This singularity lies at the heart of the black hole, and it is wrapped in a one-way veil called the event horizon. The event horizon is not a physical surface, it's a boundary. Once anything crosses it, not even light can escape. Time, space, energy, and matter all are pulled inward, never to return. From the outside, the black hole appears silent, static, and black. But what happens inside? We don't truly know. To approach a black hole is to take a journey into relativity. As you draw near, gravity warps the very fabric of space and time. Light bends, time slows. To a distant observer, someone. Falling into a black hole would appear to slow down, frozen in time just outside the event horizon. But to the person falling in, time would pass normally, until the moment of crossing, when they are lost to the cosmos forever. And yet, paradoxically, black holes are not entirely black. In the 1970s, Stephen Hawking made a stunning discovery. Black holes can emit radiation. This is now known as Hawking radiation, and it arises from quantum effects near the event horizon. In simple terms, virtual particles, those same ghostly pairs we discussed in the vacuum of space, can sometimes appear at the edge of a black hole. One particle falls in, and the other escapes. The escaping particle carries away a tiny bit of the black hole's mass, causing it to slowly evaporate over time. Yes, black holes can die. But for most black holes, this evaporation takes trillions upon trillions of years, far longer than the current age of the universe. Still, the idea that something as massive and final as a black hole can eventually disappear into a puff of radiation challenges everything we thought we knew about permanence. Black holes come in many sizes. Stellar mass black holes, formed from dying stars, may have masses a few times that of the Sun. But at the center of most galaxies lie supermassive black holes, millions or even billions of times more massive than the Sun. The black hole at the center of our own galaxy, Sagittarius A, is about 4 million solar masses. It sits quietly now, but in the past, it may have consumed stars, planets, and clouds of gas with terrifying efficiency. There are even intermediate black holes, and perhaps, at the very beginning of time, tiny primordial black holes formed in the chaos of the Big Bang. These would be no bigger than atoms, but with the mass of mountains. Some scientists speculate that dark matter, the invisible scaffolding that holds galaxies together, might be made up of these ancient mini black holes. Black holes may also be the engines of creation. Some theories suggest that the core of a black hole could birth a white hole on the other side, an object that expels matter instead of pulling it in. In this view, black holes aren't just cosmic graves. They might be the mouths of wormholes, bridges connecting distant points in space-time, or even birthing points for new universes, with each black hole spawning a separate cosmos, like seeds from a tree. Think about that. Every black hole in our universe could be a doorway to another. And then there's the information paradox. According to quantum physics, information about particles, states, and configurations can never truly be destroyed. But black holes seem to do just that. They swallow everything, leaving no trace. What happens to that information? Is it preserved on the surface of the event horizon, encoded in a kind of cosmic hologram? Is it slowly leaked back into the universe via Hawking radiation? Or does it vanish, violating the laws of quantum mechanics? This paradox lies at the heart of modern physics. Solving it may reveal the secret to unifying gravity with quantum mechanics, the elusive theory of everything. Black holes aren't just strange, they are necessary. They are the boundaries of knowledge, the wild edge of what science can touch. They force us to ask the biggest questions. What is space? What is time? What is reality? As you drift deeper into sleep, picture one, a perfect sphere of darkness floating in the fabric of space, its gravity bending starlight around it like a lens. Around its edge, hot gas swirls in a glowing halo, screaming toward oblivion. And at its center, what? A doorway? A void? A new beginning? No one knows. And that's what makes it beautiful. To truly grasp the surreal nature of black holes, we must consider what it would feel like, not just scientifically, but experientially, to approach one. Picture yourself aboard a spacecraft, slowly drifting toward a black hole's event horizon. Everything is still, silent. The surrounding stars begin to warp and curve around the object, like marbles circling a drain. As you draw closer, time slows, not for you, but for the universe beyond. The clock on your ship ticks normally, but to an outside observer, it slows to a crawl. Then you pass the event horizon, the point of no return. There are no alarms, no visible threshold. you simply cross it. At this point, all paths, all directions, all futures lead inward, downward. You can no longer escape. You are falling toward the singularity, and something even stranger begins to happen. Due to the intense difference in gravitational pull between your head and your feet, your body is stretched lengthwise and compressed side to side, a process charmingly known as spaghettification. This isn't just theoretical. If you were to fall into a stellar mass black hole, the tidal forces would be so intense that your body would be torn apart atom by atom before reaching the center. Your atoms would become part of the black hole's mass. Your information, perhaps, smeared across its horizon. But if you fell into a supermassive black hole, the story changes. Because of their sheer size, the tidal forces at the event horizon are far weaker. You might cross into the black hole without feeling a thing. In theory, you could fall all the way to the singularity in one smooth, terrifying journey, with no violent disassembly at the border. What you would see as you fall is almost impossible to describe. The sky would collapse around you. The light from distant stars would warp and bend into halos. The future would rush at you. The past would vanish. Time, as we understand it, would become meaningless. But even in the black hole's silence, it tells stories. In 2015, humanity detected gravitational waves for the first time, tiny ripples in space-time itself, caused by the collision of two black holes. These signals traveled over 1 billion light-years, barely changing. When they arrived on Earth, they stretched and squeezed space by a fraction of an atom, and our detectors, precise beyond belief, caught them. These waves are cosmic echoes, fingerprints of ancient catastrophes. They give us new eyes with which to observe the universe, not through light, but through the very shape of space. We can now hear the universe, listening to the slow, haunting song of massive objects, dancing, merging, and collapsing. And then there's the boundary between knowledge and speculation, where black holes meet philosophy. Consider this. Black holes are governed by entropy, the measure of disorder in a system. The more mass a black hole has, the more entropy it contains. This leads to the mind-bending holographic principle, the idea that all the information in a volume of space can be encoded on its boundary. In this view, the three-dimensional universe might actually be a projection of information stored on a two-dimensional surface, like a hologram. What if reality itself is just a shadow of something deeper? This idea has led to speculation that black holes, and perhaps the universe, are forms of information processes, that physics is computation, that consciousness, matter, space, and time are all emergent phenomena in a vast cosmic code, and black holes, being the most extreme processors of information, might hold the keys to this hidden language. Some physicists even propose that the entanglement of particles, a strange quantum link between two particles across space, might be related to the structure of space-time itself. That Einstein-Rosen bridges, wormholes, are physical manifestations of quantum entanglement. That perhaps space, as we know it, is woven together by a vast network of these invisible threads, and black holes are nodes in this web. And then there's the biggest question of all. What happens at the singularity? We have no idea. General relativity predicts a point of infinite density and zero volume, a mathematical singularity. But infinities, in physics, are signs that our theories have broken down. To truly understand the singularity, we need a new theory, a quantum theory of gravity, a theory that doesn't yet exist. Some imagine the singularity as a bridge to a new universe. Others see it as the end of all things. But perhaps it's something else entirely, something our minds are not yet equipped to comprehend. Black holes do not merely sit in space. They shape galaxies. They warp time. They challenge the boundaries between physics and philosophy, science and mystery. They are the places where our knowledge meets its edge and stares into the void beyond. As you lie still now, drifting towards sleep, imagine a black hole not as a monster, but as a mirror, a reflection of our deepest questions, a symbol of curiosity, an invitation to wonder. Because if black holes teach us anything, it's that the universe is stranger, richer, and more astonishing than we can ever imagine. And that's the most beautiful mystery of all. Even now, as science stretches its hands deeper into the cosmos, black holes remain silent guardians of the unknown, impenetrable, vast, patient. Yet in their quiet gravity, they hold not just matter, but memory. Consider the black hole information paradox once more. When an object falls into a black hole, be it a star, a spacecraft, or even a photon of light, what becomes of the information that describes its properties? The laws of quantum mechanics insist that information cannot be destroyed, but black holes seemingly do destroy it. They swallow everything and let nothing return, save for the slow whisper of Hawking radiation. So where does the information go? Some physicists believe it is encoded on the event horizon, preserved in a scrambled, unreadable form, etched like hieroglyphs into the surface of the black hole. This surface, this shimmering boundary, would then act like a cosmic hard drive, storing every particle, every detail, every identity that ever crossed its threshold. If this is true, then the surface of a black hole is not a featureless veil, but a library of lost stars, of fallen worlds, of everything that ever dared to touch its edge. Others suggest that the information might leak back out, particle by particle, embedded subtly in the Hawking radiation that escapes over billions of years. But no one has yet found a way to decode it. And then there's an even more profound idea. What if black holes are mirrors? Not literal reflections, but conceptual ones. What if they reflect the structure of the universe itself, its birth, its death, its nature as a mathematical reality? The singularity may be a point of infinite compression, but perhaps also of infinite possibility. A place where the fabric of reality folds in on itself and then perhaps folds outward again. This brings us to the realm of black hole cosmology. Some theorists have proposed that our universe may have originated from the interior of a black hole in another universe. In this model, each black hole is a seed, a bud from the branching tree of the multiverse. Our own Big Bang, then, could be the result of a star collapsing in a distant cosmos, birthing our universe on the other side of its singularity. If so, every black hole in our universe could be giving rise to new universes right now, a cascade of realities, each with its own laws of physics, each expanding endlessly in isolation. You and I, then, would be beings born from the death of another cosmos. Our own black holes might someday birth their own realities in turn, a cosmic ancestry too vast to comprehend. And here, in this cathedral of possibility, we find ourselves again facing the mystery of time. Inside a black hole, time and space trade roles. Time becomes space-like, inevitable. Space becomes time-like, bound by direction. All futures lead inward. There is no stopping, no turning back. This isn't just poetry. It's the actual mathematics of general relativity. The singularity is not merely a place. It is a moment in time that lies in everyone's future once inside. Yet outside the event horizon, time continues. The black hole persists, perhaps for billions of years, slowly losing mass through evaporation, shrinking toward its eventual end. When the last particle is released, and the black hole vanishes in a flicker of radiation, does the information reappear? Is it somehow restored or forever altered? Some think the final burst of a black hole's life, a final flash of light, may reveal everything it once consumed, like the closing line of a book whispered back in reverse. Others believe the mystery will remain. And now, let us imagine the most haunting idea of all, the universe itself, slowly becoming a black hole. As the cosmos expands and galaxies drift apart, as stars exhaust their fuel and collapse into silence, as black holes merge and absorb, the universe heads toward a cold, quiet fate known as the heat death. In this future, all matter is swallowed by black holes. All light is dimmed, all activity ceases. Only black holes remain, evaporating ever so slowly into darkness. Eventually, even these will vanish, leaving behind only the memory of what once was. In the final silence, the universe becomes not a place of stars, but of entropy, a sea of cold particles, a quiet hum of residual radiation, the faint afterglow of a past that once blazed with life. But here you are, alive, breathing, listening to the echoes of black holes as you rest. A creature of awareness suspended between stars, born in the blink of cosmic time. And perhaps, one day, your atoms will fall into a black hole. They will be stretched and scattered, yes, but perhaps, just perhaps, they will be remembered. The universe forgets nothing. It only waits to be understood. Time is something we all feel deeply, yet struggle to define. It guides our lives, ticks in the background of every moment, and carries us forward from past to future. But what if time isn't absolute? What if time bends, stretches, and even pauses? In the universe, it does. Welcome to the strange world of time dilation, where time slows depending on how fast you're moving or how deep you are inside a gravitational field. This idea, born from Albert Einstein's theory of relativity, changed our understanding of the cosmos forever. According to special relativity, the faster you move through space, the slower you move through time. This is not metaphorical. This is real. If you could travel near the speed of light, time for you would tick much more slowly than it does for someone at rest. This effect is tiny at everyday speeds, but at velocities near the speed of light, it becomes profound. Imagine astronauts traveling to a distant star at nearly the speed of light. To them, the trip might take only a few years. But on Earth, decades or even centuries could pass. When they return, their loved ones would be long gone. The travelers would have aged just a little. The world they left behind would be a memory. Then there's gravitational time dilation, from Einstein's general theory of relativity. It tells us that time slows down in the presence of strong gravity. The stronger the gravitational pull, the slower time moves. Near a black hole, where gravity is overwhelming, time slows dramatically. If you hovered just outside the event horizon, minutes for you could be centuries for someone farther away. This idea was beautifully illustrated in the movie Interstellar, where a crew visits a planet orbiting close to a black hole. They stay on the planet for only a few hours. When they return to their ship, years have passed for their colleague who stayed behind. That dramatic difference? It's not just science fiction, it's science fact. Gravitational time dilation has been confirmed experimentally. We've flown atomic clocks on airplanes and placed them at the tops and bottoms of towers. The clocks tick at slightly different rates, depending on their altitude, their speed, or their proximity to massive objects. Even on Earth, you are aging slightly faster at the top of a mountain than at sea level. And astronauts aboard the International Space Station zipping around Earth at 17,000 miles per hour, experience both types of time dilation, speed and gravity. They age just a tiny bit slower than we do. But these effects, while measurable, are small. To see dramatic time distortion, we need to venture far deeper into the gravitational wells of neutron stars or black holes. There, time becomes something else. A soft thread stretched thin, a whisper in slow motion. Now imagine this. What if we could use time dilation for exploration? If we had the technology to approach light speed, we could journey to distant galaxies within a human lifetime, at least from the traveler's perspective. Civilization on Earth might change completely in their absence, but they would live to see other stars, other worlds, and return with stories no one expected. Yet this gift comes with cost. Time dilation creates distance not just in space, but in memory. For a traveler, time becomes slippery, personal, private, out of sync with the rest of humanity. There's something poetic in that, isn't there? And then, of course, there's the biggest implication. If time isn't fixed, then neither is the order of the universe. The future isn't some distant destination we all march toward at the same pace. It's a tapestry, warped by gravity, rippled by speed, and unique to each observer. Even light is not immune. The same beam of light, viewed from two places, can stretch into a red glow or shrink into blue brilliance. Its time of arrival shifted by motion, distance, and gravity. In essence, time is personal. And that's not just a poetic idea. It's the reality of relativity. There is no master clock ticking for the cosmos. Every atom, every star, every observer has their own time, a lonely tick in the orchestra of the universe. So as you rest now, feel your own heartbeat, a quiet rhythm, steady and slow. It is your clock, your time. And out there, across the stars, other clocks tick too, each one different, each one real. Time is not just a river, it is a landscape, curved, twisted, and beautiful. And you, floating in this strange ocean of time, are a part of its mystery. Time dilation doesn't just challenge how we experience the passage of time, it changes what we mean when we say now. Imagine two observers, one on Earth, one traveling near the speed of light in a distant galaxy. From each person's perspective, their now is different. Their perception of time, their sequence of events, the order in which things happen, all become fluid. There is no universal present moment. Every point in space has its own clock, ticking to its own rhythm. This leads to a mind-bending truth. The past and the future are not fixed points, but part of a continuous space-time fabric. What you experience as now may be seen as past or future by someone else, depending on how they are moving or how close they are to a massive object. In Einstein's universe, time is not separate from space. It is woven together with it into a single entity, space-time, a four-dimensional reality in which time is just another coordinate, like north or south. And like space, it can be bent, curved, and shaped. Mass bends space-time. The more mass, the greater the curvature. This curvature is what we feel as gravity, and it is also what affects the passage of time. A massive planet like Earth barely curves space-time, but a black hole, a neutron star, they curve it so steeply that time itself bends downward, pulled into the gravity well. To a distant observer, someone falling into this well would seem to slow, then freeze, suspended forever on the brink. But the faller feels nothing strange. They fall, time passes, the singularity draws closer. In this way, time becomes perspective. Even light, the universal speed limit, obeys this warping. When light escapes a strong gravitational field, it loses energy and stretches into red, a phenomenon called gravitational redshift. What began as a brilliant flash may arrive as a faint whisper. The light tells a story, but the further it travels, the more the story fades. Now imagine a distant civilization, orbiting a massive star on the edge of a black hole. For every hour they experience, centuries might pass in the universe outside. In their night sky, galaxies would evolve in fast forward. Stars would be born and die. Spiral arms would twist and fade. Entire civilizations might rise and vanish. To them, the universe would seem alive, changing, growing, and decaying in real time. And to us, that world would be frozen, barely moving, its time trapped in slow motion. We could send messages, but replies would take ages. Their seconds would be our years. Communication would break. Understanding would drift. Yet both worlds would be real. Both clocks would be valid. So what does that mean for us? Tiny beings, clinging to a rock, watching the stars. It means we live not in a single universe, but in billions of personal universes, each shaped by motion and gravity. My time is not your time. The time in your heartbeat is not the same as the time between galaxies. There is no master timeline, no universal tick of the clock. There is only perspective, only the paths we take through space-time. And so, time becomes art. Time becomes choice. In some distant future, when humanity has learned to ride the waves of gravity, we may use time dilation to see into the future. By orbiting close to black holes or traveling at high speeds, we might skip ahead in cosmic history, leapfrogging eons. But we can never go back. Time, once experienced, is spent, and yet light remembers. Every photon carries with it a memory, a timestamp, a snapshot, a record of when and where it began. When we look at the stars, we are not seeing them as they are, but as they were. Some of the stars you see tonight may no longer exist. Their light is just now arriving. You are witnessing history written in particles. The cosmic microwave background, faint, uniform radiation that fills the universe, is light from just after the Big Bang. It has traveled for over 13 billion years, stretched by expansion, cooled by time, slowed by gravity. It is the oldest light in the universe, and it's still here, still whispering. So as you lie still now, breathing softly, think of this. Your body is not just matter. It is time. Every cell, every heartbeat, every moment you've ever felt, it's all inscribed in the rhythm of your own personal universe. And though time may stretch and warp and spiral, it also connects us to the stars, to the future, and to each other. Because even in the strange mechanics of relativity, there is something beautiful. The understanding that we all move through time together, even if not at the same speed. There is a quiet truth that time dilation teaches us, that every moment is relative, and therefore, every moment is precious. In a universe where time does not tick evenly, where its flow is sculpted by gravity and motion, what we call now becomes sacred. A personal truth, experienced only once, from only one perspective. But beyond the physics lies something even more mysterious: the human experience of time. How do we measure a second, a minute, a lifetime? The answer isn't just found in clocks or calendars, but in memory, emotion, and awareness. A joyful hour can pass like a blink. A moment of fear can stretch into eternity. In dreams, time unfolds without rules. A story spanning years may occur in a single breath. We wake up, astonished at how the brain reshaped the rhythm of reality. Even our biological clocks, the circadian rhythms encoded in our cells, are guided not by absolute time, but by cycles of light and dark, sleep and wake, heartbeat and breath. Time to the body is something fluid, responsive, internal. The ticking of neurons, the pulsing of hormones, the steady wave of breath through the lungs. When we experience time dilation in the cosmos, we also confront time dilation in the self. A parent watching their child grow, an artist lost in creation, a traveler on a silent road, all feel the distortion of time in their own way. It's not about physics, it's about presence, about attention, about the way we embed ourselves in a moment so deeply that it becomes eternal in our hearts. But imagine a future, one shaped not only by emotion, but by technology. What if we could master time dilation, build habitats in high-gravity wells, or construct ships that skirt near light speed? To those aboard, centuries could pass in the universe while only a few years went by within. They could leave Earth, cross the galaxy, and return to find a different world, new languages, new species, new empires, maybe even a different star in the sky where the sun once stood. This kind of travel turns time into a bridge and a wall, and yet the longing to stretch time, to reshape it, to escape it, is ancient. Myths across cultures speak of enchanted sleep, of time travelers, of beings who step into hidden realms and emerge to find the world transformed. The Rip Van Winkle of modern physics is not a dreamer in a forest, but an astronaut near a black hole, watching the universe whirl forward while they float in a deep, slow silence. And in a sense, this has already happened. On Earth today, time dilation is real and functioning. The GPS in your phone accounts for it. Satellites orbiting Earth must correct for both the slower passage of time due to their speed and the faster passage of time due to their altitude. Without these corrections, your GPS would drift off course within minutes. In this way, relativity isn't just a cosmic theory. It is something we live with, use, and rely on every day. But we don't notice it. Because time is seamless to us, we don't feel it speeding or slowing. We only feel it through change. We feel it in the way shadows stretch across the ground, in the way voices deepen with age, in the wrinkles around our eyes, in the memories that grow softer and sweeter with distance, and in sleep. When we fall asleep, our awareness of time vanishes. Dreams dissolve seconds and minutes into feeling. We awaken and ask, how long was I gone? Was it minutes, hours, a night? Time dilation, it turns out, doesn't just belong to astronauts or physicists. It belongs to every dreamer. So as you lie here now, on this quiet edge of consciousness, consider this. The flow of time you feel is yours alone. It is shaped by your heart, your breath, your thoughts. And out there, across the stars, others feel theirs too. Each one different, each one precious. The universe is a clock with no single hand, only countless tickings, soft and staggered, echoing through the dark. And tonight, your clock is still, gently ticking toward dreams. Among the most mysterious ideas in theoretical physics is the possibility that the universe is not only made of particles and waves, but of strings, not the kind that vibrate in musical instruments, but cosmic filaments that stretch across the vastness of space. These are cosmic strings, and if they exist, they could be among the oldest and most bizarre structures in the universe. Unlike black holes or neutron stars, cosmic strings are not formed from collapsing matter. Instead, they are believed to be defects in the fabric of space-time itself, left over from the earliest moments after the Big Bang. To understand cosmic strings, imagine the early universe as a vast hot soup of energy. As it cooled, like a freezing pond, it underwent phase transitions. And just as cracks form in ice as it hardens, imperfections may have formed in the universe's structure. These imperfections could have become long, thin tubes of incredibly dense energy, cosmic strings. If this sounds abstract, think of them like fault lines in space-time. Infinitely thin, but infinitely long. A single cosmic string could stretch across a galaxy or even the visible universe, thinner than a proton, yet with mass so great that it warps the space around it. The gravitational pull of a cosmic string would be immense. If two such strings were to collide, the energy released could dwarf anything humanity has ever imagined. Even more curiously, cosmic strings might not just exist in straight lines. Some could form loops, snapping off from larger strings and oscillating in space like vibrating rubber bands. These loops could decay by releasing gravitational waves, ripples in the fabric of reality. If detected, such waves would be a signature unlike anything else in physics. And yet, for all their dramatic potential, cosmic strings remain theoretical. No one has seen one. No telescope has photographed one. But the mathematics that predict them are elegant and consistent. They arise naturally in string theory, one of the most ambitious efforts to unify all of physics into a single framework. String theory proposes that the fundamental building blocks of reality are not particles, but tiny, vibrating strings of energy. Depending on how they vibrate, these strings manifest as different particles, electrons, quarks, photons, and so on. In this view, the entire universe is music, and every atom is a note in a cosmic symphony. Cosmic strings would be the large-scale echoes of this fundamental music, immense, ancient chords still humming from the dawn of time. And if they exist, they could provide clues to the unification of forces, to the very architecture of the cosmos. But their strangeness doesn't stop there. A moving cosmic string could warp space so severely that it might cause gravitational lensing, bending light into double images of distant stars. If a string passed between you and a galaxy, you might see two identical versions of that galaxy, mirrored across space. This effect could, one day, be used to detect them. Some theories go even further. Cosmic strings might serve as portals, creating shortcuts through space and time. If two strings pass near each other at high speeds, the region between them could act like a tunnel through space-time, a wormhole. This isn't confirmed science, but it's a possibility being explored by physicists. In this version of reality, strings are not just leftovers from creation, but tools for navigation, pathways through the folds of the universe. And then there's the philosophical implication. If the universe has strings, if it hums with structure, then perhaps reality is woven, not random, but textured. Perhaps the laws of nature are not just rules, but patterns. And perhaps, in the quiet of space, these patterns still vibrate with the energy of creation. Tonight, as you relax, imagine drifting beside one of these strings, stretching into infinity, silent, invisible, yet vibrating with the memory of the Big Bang. As you move along it, stars pass in your periphery. Galaxies blur. Time becomes strange. You are not just observing the universe. You are tracing its original lines, its most ancient scars. Cosmic strings, if they exist, are the bones of the universe, the lines drawn at the moment everything began. And in their mystery, we find something beautiful. A reminder that even the empty parts of the universe may still echo with the music of its birth. The idea of cosmic strings touches something primal, something poetic, that the universe might still carry tension from its birth, that the Big Bang left not only galaxies and atoms in its wake, but also these threads, tight, narrow scars across the cosmos, stretching from one end of time to the other. If these strings exist, they are not made of matter as we know it. They are topological defects, born when the universe cooled and its fundamental forces separated. In those early moments, when temperatures were unimaginably high, all the forces of nature, gravity, electromagnetism, the strong and weak nuclear forces, may have been united. But as the universe expanded and cooled, these forces began to split apart, like ice cracking under pressure. Where these splits occurred imperfectly, defects may have formed. Cosmic strings are the potential fossils of that transition, and they would be unimaginably powerful. Even a string only a kilometer long could weigh as much as a planet. One that stretches across the universe would have the energy to alter the paths of galaxies. Their tension is so great that, if released, a snapping string would unleash energy far beyond the output of any star. Physicists describe this tension as being equal to the energy per unit length, and in the case of cosmic strings, that energy is enormous, enough to warp space-time around them, bending light and gravity. The result? A cosmic string could produce a conical geometry in space, where light passing near the string is split and redirected. Unlike traditional gravitational lensing caused by massive objects like stars or black holes, this lensing would have sharp, double image features, unique signatures that scientists could detect. Some researchers have scanned the sky, searching for these double images, for sudden sharp gravitational waves, for subtle imprints in the cosmic microwave background. These are the fingerprints we expect a cosmic string to leave behind. A ripple in the oldest light, a tremor in the structure of space. So far, no clear evidence has emerged, but neither has the theory been disproven. The cosmos is vast. The strings, if they exist, could be rare, or distant, or smaller than we anticipated. Still, the theoretical framework is solid. Cosmic strings arise naturally from grand unified theories, the models that attempt to reconcile the standard model of particle physics with gravity and quantum mechanics. They are not science fiction, they are science possibility, and their implications are staggering. For example, consider a string loop oscillating in space. As it vibrates, it would radiate energy, primarily in the form of gravitational waves. These waves would ripple outward like ripples on a pond, stretching and squeezing space itself as they pass. If detected, they would be unlike anything else, distinct in frequency and pattern. And unlike gravitational waves from black hole mergers, which are sudden bursts, string loops would emit a continuous hum, like a soft, endless chord resonating in the background of the universe. In fact, some physicists believe that the mysterious stochastic gravitational wave background, a faint background buzz picked up by sensitive instruments like LIGO and nanograv, could include contributions from cosmic strings. The universe might be singing to us, we're just learning how to listen. But cosmic strings could also warp time. Due to their gravitational effects, a cosmic string could cause time to pass differently near it, like the edge of a black hole. In certain configurations, two strings moving past each other could even, according to some solutions of general relativity, create closed time-like curves, a mathematical pathway that loops back on itself. In simpler terms, a time machine. This doesn't mean we can use them to travel through time. Our understanding of causality and stability likely forbids it. But the mathematics whispers a possibility that somewhere, somehow, time itself might fold. Cosmic strings also echo something deeply human. The idea that the universe is not done yet, that the Big Bang didn't leave behind a static field, but a restless one, a living one, a universe still humming, still vibrating, still creating structure. And if we could find one, just one, it would be like discovering a signature from the birth of everything. A thread pulled loose from the original tapestry of creation. In dreams, people often speak of threads, golden ones, silver ones, silk strings that connect hearts or destinies. Cosmic strings are not so different. They are the dream threads of the universe itself, stretching across space-time, anchoring moments together, linking stars and galaxies and particles in their hidden geometry. And as you close your eyes, let yourself drift toward one. Imagine a filament thinner than an atom, glowing softly in the deep dark. It stretches on and on, beyond stars, beyond time. You float beside it, feeling its hum, an ancient vibration that speaks of beginnings, of collisions, of energy older than light. You cannot see the ends, you cannot feel the tension, but you know it is there. A line drawn not on a map, but on the bones of reality itself. And somewhere, perhaps, the universe remembers how to play the song it sang when this string first formed. We live in a universe that is, in many ways, invisible. The stars, galaxies, and nebulae we see make up only a tiny fraction of what exists. Most of the universe, its mass, its energy, its scaffolding, lies in darkness, hidden not just by distance or dust, but by design. If cosmic strings exist, they may form part of this hidden framework, not just anomalies, but structure, the literal bones of space-time. Think for a moment of a spider web stretched across a forest, invisible in the morning shadow until the light hits it just right. It glows, just briefly, then fades again into the background. That could be what cosmic strings are, webs drawn tight in the earliest seconds of time, stretching across the void, waiting for us to notice. And if they are real, they may also be ancient storytellers. A single string could have survived since the Planck era, the first 43 seconds of existence, before even gravity had separated from the other fundamental forces. In a way, such a string would not just be old, it would be primordial, older than stars, older than atoms, older than the laws of chemistry. Touching one would be like shaking hands with the moment the universe was born. It's humbling, isn't it? To imagine that as we sleep, as we live our small and beautiful lives, the cosmos holds these quiet relics just out of reach. They are not loud, they do not glow, but their influence may be everywhere. There are even more radical ideas. Some researchers have suggested that cosmic strings could be part of higher dimensional structures. In certain models of string theory, our three-dimensional universe might be embedded in a higher dimensional space, and strings, like cosmic stitches, could bind these dimensions together. These strings may reach through dimensions we cannot see or experience, connecting brains, linking realities. In such a model, A cosmic string isn't just a leftover defect. It's a bridge between dimensions, a conduit of hidden energies, a whisper from beyond the veil of the observable universe. In this sense, cosmic strings could play the role of cosmic connectors, not just across space, but across realms. Through them, the fabric of reality might communicate with itself. They may carry pulses, patterns, or vibrations that resonate across dimensions, each one an echo of the universe's deeper symmetries. Let's imagine for a moment that these strings hum, not audibly, of course, but vibrationally. Their frequencies would not be sound, but waves in space-time itself. If we could translate those vibrations into human terms, what would they sound like? Would they be low, rumbling tones like the bass of a symphony, or sharp, metallic twangs like the strings of a cosmic harp? And what if those hums, those vibrations, are carrying information? Not words or images, but raw, encoded truths. Patterns from the Big Bang, signatures of symmetry breaking, the recipe of cosmic evolution. In some ways, the universe might be broadcasting itself through these strings, not to us specifically, but inherently, because information wants to persist. Even the universe wants to remember. That's where cosmic memory comes in. If space is woven with these strings, then perhaps space itself remembers. Just as ripples in a pond remember the pebble that disturbed it, the strings might remember the moment of their creation. And not just passively, they might shape the evolution of galaxies, the bending of light, the birth of stars. Some simulations suggest that cosmic strings, if they are real, could seed structure in the early universe, that they might guide the distribution of matter, influence the formation of galaxies, and contribute to the invisible architecture of cosmic filaments, the vast webs of galaxy clusters that stretch across billions of light years. In this way, cosmic strings are not just threads in the universe. They are threads of the universe. And now, we arrive at something deeper still, something almost spiritual. Across cultures and millennia, humans have told stories of threads. The Greek fates who spun and cut the thread of life, the Norse Norns who wove the future, the red string of fate in East Asian myth, binding soulmates across time and space, the idea that destiny is woven, that fate is a fiber, that everything is connected by a thread. We feel this in our bones. Cosmic strings, in their strange way, echo this ancient metaphor. They are the universe's threads, drawn taut at the edge of time, connecting all things across the void. Not because the universe has intention, but because it has structure. Because even randomness must obey geometry. Because even chaos has form. And maybe, just maybe, the very reason we resonate with the image of a thread is that deep down, we are made of them. Not metaphorically, but physically. Perhaps the atoms in our bodies were once swept near a cosmic string, nudged into place by its presence. Perhaps the galaxies that birthed our solar system spun along one of these invisible lines. Perhaps our very lives are written across a string, singing softly in space-time. So rest now. You are a thread, too, a strand of experience, woven into the fabric of time, humming with memories of light, shadow, and breath. And out there, somewhere in the deep, dark quiet, the ancient strings of the cosmos still vibrate, waiting, singing, being. You are part of their story, and they, quietly, are part of yours. In the grand scale of the cosmos, it's easy to be swept away by things that are massive. Galaxies, black holes, cosmic strings, but perhaps the strangest, most counterintuitive phenomenon of all lies in the infinitely small. In the ghostly dance of particles deep within the quantum realm exists a mystery that challenges not just science, but our very sense of reality: quantum entanglement. At its heart, entanglement is the idea that two particles can become so deeply connected that their states remain linked, no matter how far apart they are. Measure one, and you instantly know the state of the other, even if it's on the opposite side of the universe. Albert Einstein famously called this spooky action at a distance. And despite his skepticism, this effect has been repeatedly confirmed in laboratory experiments. It's not a glitch in the math. It's not an illusion. Entanglement is real, and it is bizarre. Let's take an example. Imagine two particles created together, say, two electrons. Because they are born from the same process, their properties are entangled. If one electron spins up, the other must spin down. Now separate them. Place one in a lab on Earth and send the other to a distant planet light years away. The moment you measure the spin of the first, the second one's spin is instantly determined, even though no signal could have traveled between them. It's as if the particles are not just separate entities, but two aspects of a single deeper reality. What's more unsettling is that this connection doesn't fade with distance. It isn't weakened by time or obscured by interference. It is a connection outside space and time, immune to the limitations of light speed. This leads to the idea that the universe is non-local, that things are not just influenced by what's next to them, but by what they are deeply entangled with, no matter the separation. Entanglement, then, might not just be a feature of particles. It could be a feature of the universe's architecture. Some physicists suggest that entanglement builds space-time itself, that the reason space is smooth, continuous, and curved isn't because of some underlying geometry, but because of the web of entanglements connecting particles and fields. In this view, space is a consequence of connection. Even more astonishing is that entanglement may be related to wormholes, a bold idea known as EPR, named after Einstein-Rosen, wormholes, and Einstein-Podolsky-Rosen, entanglement, proposes that entangled particles may be connected by tiny wormholes, too small to detect. That when you entangle two particles, you are creating a microscopic bridge in space-time. This is not yet proven, but the math works, and the possibility is thrilling that every pair of entangled particles is joined by a thread, a bridge through the quantum foam of reality. And this isn't limited to theory. Entanglement is already being used in quantum computing, where bits of information are encoded in entangled particles. These systems can perform calculations at speeds far beyond traditional computers. And in quantum encryption, entanglement ensures that information cannot be intercepted or copied without disturbing the system, a perfect secrecy guaranteed by the laws of physics. But it also raises haunting questions. If particles can be entangled across space, could consciousness, could minds be entangled? Could memories? We don't know. But the metaphor is compelling, that people, like particles, may form bonds that persist across time and distance. That even when separated, something invisible remains, a presence, a connection, a whisper in the silence. And perhaps that's why entanglement resonates so deeply. It reminds us of love, of memory, of loss. The way someone can leave a room or a life but still remain in our thoughts. The way a single scent can bring back a flood of emotion. The way we feel connected to people across oceans, across years. It may be metaphor, it may be more. Tonight, as you sleep, Imagine the space around you not as empty, but as a lattice of connections, threads too fine to see, binding every particle, every star, every moment. You are not separate. You are part of a web, a universe not of isolation, but of relationship. Quantum entanglement tells us that the universe is not built from things, but from connections. And you, right now, breathing quietly, resting gently, are entangled too, with light, with memory, with all that has ever been. To truly feel the strangeness of quantum entanglement, we must let go of everything we thought we knew about separation. In our everyday world, separation means distance. A cup across the table is not the same as the cup in your hand. A star in the night sky is not the same as your breath. But in the quantum world, these boundaries begin to dissolve. Entanglement is not a thread in the ordinary sense. It doesn't stretch through space like a cord between cans. It transcends space, and it ignores time. When two particles are entangled, their relationship is instant and absolute. Measure one, and the other reflects the result. Perfectly, immediately, and yet no signal travels between them. This is the heart of the paradox. The measurement on one side seems to decide the outcome of the other, but no communication occurs. This means entanglement doesn't transmit information faster than light. It simply is. So how do we make sense of this? One way is to imagine that the entangled particles are not two things at all, but one, a single state split across space. A unity expressed as a duality. In this way, space becomes a kind of illusion. What we perceive as here and there are just projections of a deeper, more connected reality. This challenges the very foundation of local realism, the belief that physical processes occur independently in localized spaces, and that objects exist with definite properties, whether or not we observe them. Entanglement shatters this. In its wake, we're left with the idea that observation creates reality, that the act of looking changes what we see. And not just in theory. Entanglement has been tested thousands of times. In one landmark experiment, photons were sent through miles of fiber optic cable. When one was measured, the other's state was instantly known, despite the distance. The results weren't just correlated, they were mathematically perfect. This correlation persists even if the detectors are randomized, even if the experiment is split across mountains, even if no information could possibly travel between the measurements in time. We call these tests Bell experiments, and they confirm one thing again and again. The universe is not local. It is not built from isolated parts, acting independently. It is built from relationships, and that changes everything. If the most fundamental elements of the universe, its electrons, photons, quarks, are not separate, but entangled, then we are forced to ask, what else is entangled? Could larger systems, molecules, cells, even brains, maintain entanglement? The physics is not yet clear. Maintaining entanglement becomes harder as systems grow more complex. Decoherence, interaction with the surrounding environment, tends to break these delicate links. But new research in quantum biology suggests that some biological processes might preserve entanglement long enough to be meaningful. Birds may use it to navigate with Earth's magnetic field. Photosynthesis may rely on quantum coherence to harvest energy efficiently. And who's to say it ends there? We are made of quantum matter. Every atom in our bodies once danced in stars, bathed in cosmic radiation, and perhaps, once, entangled with other atoms still drifting through the universe. Could remnants of those ancient relationships still echo in our structure? Could the human mind, so finely balanced, so mysterious, operate in ways we haven't yet dreamed? Entanglement makes us rethink boundaries, not just in physics, but in meaning. It's why some philosophers and scientists now view the universe as a relational system, not a collection of things, but of interactions. What exists, they say, is not the object, but the connection, not the individual, but the relationship. In this view, to exist is to relate. You are not just a body, you are a nexus, a point where fields, particles, history, and memory converge. You are a story unfolding, not alone, but alongside every other story. And if entanglement is real, not just physically, but as a principle, then perhaps we are entangled too, with each other, with the past, with every moment we've touched and everyone we've loved. Because love too feels like entanglement, doesn't it? It makes no sense in a world of pure causality. It reaches across distance, defies time, resists reason. When you think of someone long gone and still feel their presence, when a voice, a scent, a moment takes you back, instantly. When you dream of someone you haven't seen in years and wake up with your heart beating fast, is that not a kind of entanglement? Maybe the universe teaches us something subtle through quantum mechanics. That connection is more fundamental than form. That what binds us is not matter, but memory. Not position, but presence. So now, as sleep calls you deeper, picture the space around you, not as empty, but alive. A quiet, invisible lattice of entangled particles reaching across your room, your planet, your galaxy. You are not alone. You are woven in. You are entangled with light, with thought, with everything that has ever existed. And as the night deepens, know this: the universe does not forget its connections, and neither do you. Imagine standing alone in a dark room. There is silence, stillness. You stretch out your hand, and somewhere, unseen, another hand moves. Not because it sees you or hears you, but because it is entangled with you. This is the quiet poetry of quantum entanglement. It defies not only physics, but intuition. It rewrites our idea of what it means to be separate. Two particles, born together, do not forget each other. They do not drift into silence. Even as space between them stretches into light years, their connection remains perfect, immediate, and total. In a universe where everything began at a single point, an infinitely dense moment we call the Big Bang, everything was once connected. Everything was once entangled. This means that, in theory, the particles in your body are still linked, however faintly, to particles on the far side of the cosmos. Entanglement doesn't fade with distance. It is not bound by location. If you were once part of the same state, you are always part of the same story. And isn't that a beautiful thought? That the universe isn't just made of stars and atoms, but of remembrance. That separation is an illusion built from the limits of our senses. That everything we love, everything we have touched, may still be touching us, through hidden bonds we can't measure, but somehow still feel. Entanglement is also a mirror. It shows us that what we see depends not only on the object we observe, but on the entire system. That reality is not composed of individual things, but of relationships. When you measure one part, you change the whole. When you touch one strand, the web quivers everywhere. And this understanding is not confined to the subatomic. It reaches into systems of all kinds, networks of neurons, ecosystems of living things, and yes, even the delicate patterns of human interaction. It's why we speak of chemistry between people, of intuition, of invisible bonds. It's why a song written by someone long dead can still move you to tears. Why a memory of someone far away can warm you, comfort you, even guide you. These moments are not accidents. They are echoes. They are resonances. Perhaps, in ways we have yet to understand, our lives are entangled, not just with others, but with moments, with dreams, with futures still unwritten. And this is what makes entanglement more than science. It makes it metaphor. It makes it myth. Because the deeper we look into reality, the more we find that the fundamental forces of the universe are not separation, but union. That the great engine behind stars and galaxies might not be chaos, but connection. And perhaps, when we quiet ourselves enough to listen, truly listen, we can feel that connection, not as a sound, but as a certainty, a stillness, a gentle reminder that we are never truly alone. Tonight, as the stars wheel silently overhead, remember this: somewhere, something is entangled with you. And that bond, though unseen, is unbroken. Sleep, then, not as an island, but as a thread in a vast and wondrous web, glistening, breathing, alive. If black holes are the ultimate act of cosmic collapse, then neutron stars are the halfway mark. Strange, beautiful remnants of massive stars that died not with a vanishing, but with a scream. They are the most compact stars in the known universe. What remains after a supernova when gravity crushes matter into something that defies logic, but not law? To understand a neutron star, you must imagine something the size of a city with the mass of a sun. A sphere only about 12 miles across, small enough to drive across in half an hour, but so dense that a single teaspoon of its material would weigh around 1 billion tons. This is matter at its most extreme. Atoms, as we know them, no longer exist here. The force of gravity is so powerful that electrons and protons merge into neutrons, creating a star made almost entirely of one particle. The result is a kind of cosmic crystal, a star-sized nucleus, a relic of collapse frozen in time. Their magnetic fields are millions of times stronger than Earth's, and their surface gravity is so intense that if you stood on it, if you could, you would be crushed instantly, your very atoms warped into new forms. And yet, within this violence lies elegance. Neutron stars spin rapidly, like ballerinas pulling in their arms. Some rotate hundreds of times per second, flashing beams of energy like lighthouse beacons through space. These are known as pulsars, the ticking clocks of the universe. Pulsars are so precise in their rotations that we can measure their pulses like seconds. Some are even more stable than atomic clocks. When we first discovered them, the regularity was so startling, scientists thought they might be signals from alien intelligence. They called the first one LGM-1, short for Little Green Men. But these were no messages. They were the last heartbeat of dead stars, echoing into the void with unfathomable regularity. Yet, neutron stars are not just static monuments. They can change, they can collide, and when they do, when two neutron stars spiral into each other in a death dance of gravity, they create an explosion more powerful than 1,000 supernovae. This collision, called a kilonova, produces gravitational waves detectable here on Earth. And even more wondrous, it forges elements like gold and platinum. That's right, many of the heavy elements in your jewelry, your electronics, your bones, were born in the collision of stars so dense that they crushed space and time. The ring on your finger may have once been stardust, forged in a neutron star's funeral pyre. But the strangeness doesn't end there. Inside a neutron star, the laws of physics are pushed to their limit. We don't fully understand what happens at their core. It could be a soup of neutrons. It could be quark-gluon plasma, a state of matter from the earliest universe. It could even be something entirely unknown, something we haven't yet named. Some theories suggest the existence of strange stars, made not of neutrons, but of even smaller particles called strange quarks, creating a substance denser than anything we've ever conceived. These would be like neutron stars, but more compact, more massive, and perhaps even more stable. And then there's the quiet terror of magnetars, a rare kind of neutron star with magnetic fields so strong that they can twist atoms apart from miles away. If a magnetar passed within 1,000 kilometers of Earth, it could erase every hard drive on the planet. A burst from a magnetar was once detected from 50,000 light-years away, and it still disrupted satellites in Earth orbit. These stars are, quite literally, dangerous to know. Neutron stars challenge our sense of scale, our understanding of matter, our very intuition about what's possible. They sit in the middle ground between the visible and the invisible, the tangible and the unimaginable. They are what happens when the universe tries to say, almost, when a star collapses, not all the way into a black hole, but stops just before the brink. And yet, they are still storytellers. Their pulses mark time in the cosmos. Their collisions seed galaxies with gold. Their magnetic fields bend light and thought alike. And their mystery, dense, hidden, silent, invites us to ask deeper questions. What happens to matter when everything we know is stripped away? What becomes of a star when it dies, but does not disappear? Tonight, as you breathe slowly and drift further into stillness, imagine yourself aboard a spacecraft drifting silently toward one of these stars. The sky darkens, the pinprick grows brighter. You see it spin, flash, whisper in its light. You feel the pull, not just of its gravity, but of its story. A story of collapse, of pressure, of beauty born in extremity. You're not afraid, you're in awe. Because in the silence of a neutron star, you can hear the memory of fire, the echo of time, the music of pressure turned to permanence. To speak of neutron stars is to speak of contradiction. They are both dead and alive, cold and blazing, still and spinning faster than the eye can track. Their surfaces are deceptively quiet, while their interiors boil with uncharted forces. They are not merely objects in space. They are equations made real, built from the residue of celestial death, governed by rules we are only beginning to understand. Let us begin with gravity. A neutron star is not only dense, it is an altar to gravity. The force at its surface is so strong that it warps space-time dramatically. Light emitted from the surface doesn't travel straight, it curves. Photons lose energy just to escape. If you were to stand on the surface of a neutron star and somehow survive, you would see the sky bent, distorted. The entire star beneath your feet would seem to curve upward, allowing you to see far more of its surface than a normal sphere would permit. It is as though the star folds space around itself like a cloak, and time, it slows here. To a distant observer, a clock on a neutron star ticks slower than one in open space. This is gravitational time dilation, but at an extreme. The star doesn't just pull at your body, it pulls at your moments. Seconds stretch, fall behind. The star compresses everything: mass, energy, light, time itself. It is a knot in the fabric of the cosmos. Now imagine the crust, a term that feels almost too gentle for something so alien. The outer layer of a neutron star is thought to be the strongest material in the universe, billions of times harder than steel. It is a lattice of nuclei packed so tightly that a single crack, a starquake, can release more energy than 1 billion atomic bombs. These starquakes send tremors through space-time, possibly detectable by future gravitational wave detectors. They may also unleash bursts of gamma rays, flickers of deadly light traveling across the galaxy. Beneath the crust lies mystery. There, neutrons swim in a quantum ocean. A superfluid, frictionless, silent, and strange. Imagine a sea where motion never stops, where particles move in synchrony, forming vortices that spiral with perfect precision. This is not science fiction. This is quantum reality. The interiors of neutron stars may be among the only places in the universe where such superfluids exist at large scales. Somewhere deeper still, things grow more uncertain. No experiment on Earth can replicate the pressures here. The theories begin to diverge. Some physicists believe that deep in the heart of a neutron star, neutrons may dissolve into their constituent quarks, forming a quark star or a hybrid star with layers of both neutrons and free quarks. If this is true, we may be seeing the formation of new types of matter, new states of being. Others go further. They propose strange matter, composed of strange quarks, more stable than the matter we know. A single droplet of strange matter could theoretically convert ordinary matter into more of itself. If strange matter exists and is ejected from a neutron star, it might convert anything it touches, turning stars, planets, even people, into strange stars. This is not a confirmed possibility, but it's a serious one, and it raises a strange question. Is our universe hiding different forms of matter, built not from atoms, but from something more exotic? Then there's the possibility of binary neutron stars, pairs locked in a spiral dance, orbiting closer and faster until they collide. These collisions are among the most spectacular events in the universe. The 2017 observation of such a merger, known as GW1708-7, was a landmark moment in astrophysics. For the first time, scientists detected both the gravitational waves and the electromagnetic light from the same event. This single moment confirmed decades of theory that neutron-star collisions forged the universe's heaviest elements: the gold in your wedding ring, the uranium in a reactor, the platinum in a satellite. These may all have been born in that moment of union and destruction. But perhaps the most haunting aspect of neutron stars is not their violence, but their stillness, their silence. These stars no longer burn with fusion. Their fuel is gone, and yet they persist, spinning, glowing, echoing. They are not fiery engines like our sun. They are fossils, spinning with the memory of light. In this way, neutron stars are monuments to resilience. They endure. Their forms are strange. Their voices are quiet, but they last. Some may spin for billions of years, gradually slowing until they become cold, dead embers of quantum matter. In the far future, when all the stars have faded, when black holes evaporate into nothing, neutron stars may still exist, dim, cold, and alone in the dark, but not forgotten. Because to find one is to remember. To detect its pulse is to know that something once lived, once exploded, once refused to vanish. So now, as sleep takes you further into stillness, imagine yourself within the orbit of a neutron star. Feel its gravity, not crushing, but grounding. Feel its pulse, not loud, but constant. Let its strange matter be your anchor. Let its steady rhythm be your breath. And in that silence, know this: you are resting within a universe that remembers, a universe where even death leaves a mark, where even collapse can become a song. To ponder neutron stars is to confront the intersection of the familiar and the unfathomable. These remnants, formed from destruction, represent a kind of cosmic memory, a place where history is not written in ink or light, but carved in gravity, etched into the lattice of space itself. They are the residue of life cycles far beyond our scale, the skeletal remains of stars that lived fast, died violently, and refused to disappear. And perhaps they are more than that. Perhaps neutron stars are the dreams of the universe, frozen in time. What happens to matter when it is stripped of complexity, of identity, of the very architecture that gives it form? What's left when atoms collapse, when electrons and protons lose their individuality and merge into something homogeneous? What remains is simplicity, but a simplicity born from depth, not absence. A neutron star is almost pure neutron matter, yes, but those neutrons contain within them all the forces, all the symmetries, all the echoes of the universe's creation. They are not dead, they are quiet. We often imagine stars as beacons, radiating life, but neutron stars radiate meaning. Their very existence forces us to rethink what is possible. They compress the universe's rules into a sphere of paradox, motion without fusion, mass without size, time without constancy. And still they spin. This rotation, rapid, perfect, unyielding, is not just a feature, it is a voice. These stars, though dead in the traditional sense, speak. They pulse. Some slow with time, others speed up after absorbing matter. Some blink in and out, disappearing and returning with mysterious regularity. Their timing can be so precise that we can use them to navigate spacecraft, to study the curvature of space-time, to test the very edge of Einstein's equations. But beyond the physics, they hold a kind of metaphor, that even in the aftermath of collapse, there can be order, that from destruction can come pattern, that what seems like an ending may become the most perfect form of presence. And if neutron stars can persist, if they can hold the memory of motion, of mass, of magnetism, what might we hold? What might humans carry deep within us from our own collisions, from the pressure we endure, from the moments where we feel broken, compressed, silenced? Perhaps, like neutron stars, we also contain a strange stillness, a dense resilience, a signal so faint it's often missed, but so consistent that it lasts far beyond the chaos that created it. So tonight, imagine this, drifting above the surface of a neutron star, hovering at the edge of time. You look down and see the light curve, not just the beams of radiation, but the distortion of time itself. You feel your seconds stretch, your weight increase, your thoughts slow into stillness. Around you, the star hums, deep and low, like the memory of a bell still ringing after it's been struck. You are not afraid. You are at peace. Because in this moment, you feel what the universe feels: gravity and grace, density and silence, collapse and continuity. The neutron star, once a violent flame, now simply is. Not shining brightly, not erupting, not expanding, but holding, remembering, spinning. And as you fall asleep tonight, let that be your rhythm. Hold, remember, spin. In the vast silence of the cosmos, let the memory of fire guide you through the night. We have mapped galaxies. We have charted stars. We have measured the temperature of ancient light and watched supernovae explode like celestial fireworks. But amid all this understanding, there remains a mystery, silent, subtle, and utterly unnerving. A mystery that defies our expectations about how the universe should behave. It is called the dark flow. To understand the dark flow, we must first look at how the universe moves. Galaxies don't just sit still, they drift, pulled by gravity. In a way, every galaxy is like a leaf floating on the surface of a pond, nudged this way and that by invisible currents. Some of these motions make sense. Galaxies fall toward clusters. Clusters pull on each other. The web of gravity shapes the dance. But in the early 2000s, scientists using data from the Wilkinson Microwave Anisotropy Probe, WMAP, noticed something strange. Some clusters of galaxies, spanning billions of light years, were all moving in the same direction. And not just slightly. They were streaming toward a specific region of space, faster than gravity alone could explain, like a current pulling them from outside the known universe. This strange motion was dubbed the dark flow, a massive, coherent drift of galaxy clusters, flowing toward a point beyond the edge of what we can see. And no one knows why. This flow cannot be accounted for by the known mass in the observable universe. It is not random. It is not noise. It appears to be a real phenomenon, and yet it suggests something profound, that our universe may not be all there is. The implication is staggering, that the universe, our entire cosmic horizon, may be just a bubble in a larger structure, that there are other regions, other universes, other cosmic domains beyond our observational reach. And something in that other domain, some massive structure, some gravitational anomaly, might be pulling on our universe, distorting our space like a hand pressing against the fabric from the other side. This idea falls into the realm of the multiverse, a theory that suggests our universe is just one of many, each with its own laws, its own particles, its own birth and death. These universes may coexist in higher dimensional space, like bubbles in a vast cosmic foam. Most would be invisible to us, but if they press close, their gravity might leak across, causing effects like the dark flow. Another possibility is that what we see is not caused by an outside universe, but by defects in space-time. Massive structures like cosmic voids or walls left over from inflation, the rapid expansion of the universe after the Big Bang. These relics, if they exist, might warp space subtly, nudging galaxies off course. And yet, no matter how we try to explain it, the dark flow remains unresolved. Some newer observations question its significance, while others confirm its direction. But no theory can yet explain it with certainty. And in that uncertainty lies something powerful, because science thrives not on answers, but on questions, on phenomena that don't fit, on whispers in the data. The dark flow is one such whisper. It says, look again, look beyond. Don't assume the map is the territory. It reminds us that the universe may be larger than our comprehension, that our observable cosmos, those 93 billion light years across, might be just a sliver of a grander, hidden whole. That there are boundaries we have not yet breached, and forces we have not yet named. And maybe that's what makes the dark flow so haunting. Not just its scale or its direction, but its suggestion of the unknown, of motion beyond reason, of pull without a source. As you lie quietly now, breathe in this idea that even the universe drifts, that it too is being pulled, not by noise, not by accident, but by something outside our view, something vast, something silent, something real. The galaxies do not panic, they simply go. They glide along the current, they follow the gravity, and they do not ask where the current leads. So tonight, neither should you. Let yourself be pulled gently into mystery. Let yourself drift like a cluster of stars toward the horizon of knowing. Let the dark flow carry you, not into fear, but into wonder, because what lies beyond may be terrifying, or it may be beautiful, or it may be something we do not yet have words to describe. In the stillness of night, when the sky stretches endlessly above us, it's tempting to think of space as a vast and finished thing, a stage already set, the lights all on, the play in motion. But every so often, something arrives that shakes that illusion. Something that says, there is more. The dark flow is such a message. The idea that entire clusters of galaxies, massive collections of stars, dust, and dark matter could move in unison toward a part of the cosmos we cannot see suggests a deeper architecture, a pattern drawn not on the canvas of space, but behind it. It's as if the observable universe is only a page in a book, and the flow we see is the breeze of turning pages from chapters yet unread. This flow is not chaotic, it is directed. It follows a path, it suggests a source. But what source could be so powerful as to sway billions of galaxies, to cause a collective drift through space that defies the gravitational map we've so carefully constructed? One answer lies in the concept of cosmic inflation, that split-second expansion after the Big Bang, when the universe grew faster than the speed of light. This event could have seeded the fabric of reality with massive structures far beyond our view. Regions of density that remain hidden, but not uninfluential. If inflation created these structures, then the dark flow might be their shadow, tugging at our space across an unfathomable gulf. Or perhaps it is not a structure, but a tear, a scar in the fabric of space-time, where geometry behaves differently, where the rules bend and curl. This could be a relic of a brain collision in higher dimensional space, a memory of our universe's violent origin, still echoing in the push and pull of galactic migration. The unsettling part is not that we can't see what lies beyond, but that we can't ever see it. The edge of our observable universe is not a wall, it's a limit of time. Beyond that, the light has not had enough time to reach us. It is not that space ends, it's that our window into it closes, and yet, through the motions of galaxies, we glimpse that shadow. We feel the brush of something enormous and unknown. This is what makes the dark flow not just an anomaly, but a revelation. It reminds us that knowledge is bounded, but mystery is infinite. That every map is provisional, that even when we think we've charted the stars, something deeper stirs beneath. And maybe that's the lesson, that the universe is not a solved puzzle. It's a living story, one that evolves, one that unfolds slowly, like a dream too big to hold all at once. The dark flow is a turning page, a breath from a place beyond understanding, a current that tells us, keep going. Philosophers have long wondered if we live inside a simulation, or a thought, or a dream of something larger. The dark flow, in its mute insistence, hints that the universe may indeed be nested, one reality within another, each feeding into the next. It may not matter if we ever know what causes the dark flow. What matters is that we see it, that we acknowledge that something beyond our reach has shaped our path, that we are part of a motion whose source we may never touch, and yet we drift, we go forward, just like those galaxies, carried by a current beyond understanding. Tonight, imagine yourself among them, a passenger in a galaxy, one speck among trillions, moving silently across the dark. You cannot steer, you cannot stop, but you can wonder, You can feel the direction of the pull. And you can trust that even in mystery, there is meaning. The dark flow is not a warning. It is an invitation to explore, to imagine, to dream without borders, to believe that the universe, in all its vastness, still has secrets to tell. After all the spiraling galaxies, the collapsing stars, the hidden strings, the whispers between entangled particles, and the invisible current of the dark flow, we are left with one question. What does it all mean? The cosmos is vast, not just in size, but in depth, in complexity, in wonder. And when we explore its most bizarre phenomena, we are not just learning facts about black holes or cosmic strings or neutron stars. We are brushing up against the mystery of existence itself. Because what is the universe really? It is not a place. It is a process, a breathing, unfolding act of becoming. Galaxies do not simply exist. They emerge. Stars are born, live and die. Particles appear from nothing, vanish into silence. Gravity curves space. Light carries memory. And from this complex orchestra of motion and matter, we, small, fragile creatures, arise. We are not observers. We are participants. We are built from stardust, yes, but more than that, we are patterns shaped by ancient forces. Our blood contains iron forged in supernovae. Our bones carry calcium that once drifted between stars. Our thoughts run on chemical reactions powered by photons from a sun 93 million miles away. And so, when we contemplate the universe, we are not looking at something other. We are looking at ourselves, reflected on a cosmic scale. This is why the strange phenomena we've explored matter. They are not trivia. They are symbols, markers of how the universe behaves when it is pushed to its limits. They are the corners where the familiar laws of physics stretch, bend, or break. And in those corners, we find beauty, not because we understand them, but because they invite us to understand. Take quantum entanglement. It shows us that the universe is not made of isolated things, but of relationships. That what matters is not the object, but its connection. That something measured here can affect something measured there. This is not just physics, it's philosophy. It's a challenge to the idea of separateness. It is a whisper. Nothing is truly alone. Take neutron stars. They show us the resilience of matter. That even after a star dies in fire and collapse, it can still endure, dense and silent. A beacon not of light, but of memory. A song not of heat, but of spin. They remind us that endings are not erasures. That pressure can create new forms, or cosmic strings. These filaments, if they exist, are not just leftovers from the Big Bang. They are history, tension, resonance, vibrating still from the moment of creation. If the universe has strings, then perhaps it has a melody. Perhaps it is singing a song we have not yet learned to hear. And then there is the dark flow, that silent, steady drift towards something beyond what we can observe. It speaks to our deep knowing that we do not have the whole picture, that no matter how much we learn, there is always a horizon, a boundary we cannot cross, a veil we cannot lift, and yet we feel the pull. And maybe that is enough. Maybe we don't need all the answers. Maybe the beauty lies in the mystery, in the search, in the quiet, patient unfolding of understanding. Think of how long it took us to realize the Earth orbits the Sun, how long it took to see galaxies as separate islands of stars, how recently we detected gravitational waves, ripples in space caused by collisions we never imagined we could observe. Every decade, the universe gives up another secret, and always the secrets are stranger than we expected. This is the nature of truth. It is not neat. It is not simple. It is wild and vast and alive. And so is the universe. So are you. As you lie here now, heart steady, breath slow, you are part of that unfolding. Your neurons fire with patterns shaped by evolution, chemistry, and memory. You are a vessel of awareness, afloat in space-time. You are an eye the universe has opened to look back at itself. Because perhaps the universe does dream of itself. Perhaps these strange phenomena, these black holes, these strings, these pulses and flows, are the thoughts of the cosmos. Perhaps, when a star collapses or a particle entangles, the universe is learning. Perhaps we are its voice, its mirror, its breath. Or maybe not. Maybe it's simpler than that. Maybe the universe is just what it is, vast, beautiful, and wild. A place where stars explode and particles dance, where gravity curves space and time, stretches and light remembers. But even if that's all it is, it's enough. Because in the end, we are here. We exist. We think. We wonder. And in that wonder, we become something more. So rest now, traveler of thoughts. Voyager of galaxies within the mind. Let the stars turn above you. Let the strange truths drift through your dreams. And when you wake, may you carry with you not just knowledge, but awe. Because the universe is not done, and neither are you.